Okay, today we're starting a new unit called Acids, Bases, and Salts. We're going to divide this unit up into two parts, 8A and 8B. And we're going to start with a good honors review. We're going to start by reviewing things that you may have learned in honors, pH, POH. In addition, we're going to learn KW, water equilibrium, and pKW. Okay, so the first thing we're going to talk about is equilibrium and water. Okay, water will auto-ionize, okay, meaning it will ionize itself. Okay, I'm writing self-ionization, but what I mean is auto-ionization. What that means is it'll react with each other, okay, or dissociate each other to make the hydronium ion and the hydroxide ion. And it's called auto-ionization. Okay, so water plus another water molecule will make hydronium and hydroxide ions. Okay, this happens to be an endothermic reaction. Okay, and remember, endothermic reaction means that the delta H will go on the reactant side. Okay, now with this equilibrium in water, okay, we have to make sure we understand our states of matter. Okay, so we have two liquids that are pure substances and then two aqueous ions on the product side. Okay, so we can actually write our law of mass action for this particular equilibrium in water. And that is KW equals the concentration of hydronium times the concentration of hydroxide. And that value actually equals 1.0 times 10 to the negative 14th. And this value, along with this formula, this law of mass action, was actually on your honors reference sheet in the pH section. Okay, and this equilibrium, like I mentioned earlier, is endothermic. So what does that mean for KW at other temperatures? This is for 25 degrees, but what about at higher temperatures? Okay, so just to review what we've learned so far with equilibrium, we've learned Kc, okay, which is based on concentration, equilibrium pressure, so Kp, K solubility product, KSP, and now we have KW, the equilibrium of water. And remember, the formulas that you use are exactly the same, products over reactants raised to whatever coefficient power. Okay, let's look, since we know it's an endothermic reaction, remember the delta H will go on the reactant side of the equation. So what would happen if instead of at 25 degrees Celsius, you increased the temperature of this reaction? Well, for Le Chatelier, remember, if you add temperature, you shift away from the delta H. Since the delta H is a reactant, it will shift to the product side. Therefore, if the concentration of H3O goes up, concentration of OH will go up, and our KW will go up. So just to repeat, as temperature is increasing, the reaction will shift to the product side, making more H3O, making more OH ion, and increasing the KW. So higher temperatures, higher KW. Okay, what would happen instead if temperature decreased? Well, think about it. If you take temperature, you're going to shift toward the delta H, and since it's an endothermic reaction, it's going to shift left. Your concentration of hydronium will go down, your concentration of OH will go down, and hence your Kw will also go down. Okay, so temperature and Kw are directly related for this endothermic reaction, equilibrium in water. Okay, so back to our slide, summarizing everything. Now, we can do an ice table showing this equilibrium. Okay, with the ice table, remember, with pure liquids, we do not include them in the ice table, just like solids, we do not include it. So I will cross out the waters when I do my ice table. Okay, and of course my initial concentrations of my products will be 0. Okay, my change, since it's a 1-to-1 ratio, will be plus X, just like we did in our last unit. And then our total, which is our initial plus our concentration, will be X. So you can see that if we plug X into our Kw equation, we will have X squared equals 1 times 10 to the negative 14th. If we solve for X, we could take the square root of 1 times 10 to the negative 14th, which is 1 times 10 to the negative 7th. Okay, now we're going to learn what that 1 times 10 to the negative 7th means. Okay, so let's first talk about an acidic solution. An acid is defined as anything that increases the concentration of that hydronium ion and is greater than 1 times 10 to the negative 7th molar. Okay, from the last unit we know that if that concentration of hydronium increases, then the OH must decrease. Okay, so at 25, the product of the two's got to still be equal to Kw equals 1 times 10 to the negative 14th. Okay, so an acid is anything that increases the concentration greater than 1 times 10 to the negative 7th. Okay, now just be careful of your exponents. Okay, so remember, like a negative 5 as the exponent is a bigger number than 10 to the negative 7th. Okay, so watch those negative numbers. Okay, know that 1 times 10 to the negative 5th is greater than 1 times 10 to the negative 7th. Okay, so just be careful of that. All right, let's define a basic, or we can also call it an alkaline solution. Okay, a base is anything that increases the hydroxide concentration to greater than 1 times 10 to the negative 7th. Okay, and as a result, we know from the last unit, okay, if we increase the amount of hydroxide, then we know that the hydronium must decrease. Okay, so that the product of the two is still equal to 1 times 10 to the negative 14th. Okay, so just to reiterate, OH being greater than 1 times 10 to the negative 7th would be a basic or an alkaline solution. Okay, I'm just going to show you real quick from honors, just a little review, just in case you forget that hydronium concentration is also equal to the H plus. Now remember, H plus is actually hydrogen that gave away its electron. Okay, we call it a proton. Okay, so let's take an example. If we have hydrochloric acid, okay, which we can draw our Lewis structure for, and water, okay, which we can also draw our Lewis structure for. It's a bent shape, 2 lone pairs on the oxygen. Okay, what ends up happening is that hydrogen comes off of the chlorine, okay, and actually connects to a lone pair on the oxygen, making the hydronium ion. Okay, now because the mole ratio between hydrogen or proton, okay, and hydronium are the same, we can count them as both the same. Okay, so we always say that the concentration of H plus is equal to the concentration of H3O plus. We said that in honors, and that also applies in our AP course. Okay, so let's get to the nitty-gritty. So if we know the concentration of hydronium, H3O plus, we can calculate the hydroxide concentration by using the law of mass action and vice versa. Okay, so we have 2 example problems here. Okay, we have a solution that was determined to have a hydronium concentration of 4.2 times 10 to the negative 5th. What is the hydroxide concentration? And is this an acidic or an alkaline solution? Well, let's write our given down. We know hydronium is equal to 4.2 times 10 to the negative 5th molar. Okay. We can use that law of mass action to calculate the hydroxide. So let's write down our law of mass action. Okay, now before we do that, actually, I'm going to look at that concentration of hydronium, and I see that 4.2 times 10 to the negative 5th is greater than 1 times 10 to the negative 7th, therefore it's acidic. Okay, so now I'm going to use the law of mass action, which I'm writing in black. H3O plus times OH negative equals 1 times 10 to the negative 14th, to solve for OH, since I know the concentration of hydronium. Okay, and when I do that, I'm going to take that 1 times 10 to the negative 14th divided by 4.2 times 10 to the negative 5th, which is my hydronium concentration. And I'm going to get my answer. I'm going to get my answer of 2.38 times 10 to the negative 10th molar. Okay, so you can see that the hydronium is definitely greater than 1 times 10 to the negative 7th, and the hydroxide is definitely less than 1 times 10 to the negative 7th. Okay, which makes it an acidic solution. Okay, we can look at the next problem here. A solution is determined to have a hydroxide concentration of 3.2 times 10 to the negative 10th. Let's determine the hydronium concentration and indicate it if it is acidic or basic. Okay, so pause it and see if you can do it in yourself. and then we'll solve for the answer together. Okay, so the first thing is, let's write down our given, and in this case, we know our hydroxide concentration. So we have that. Okay, now because that hydroxide concentration is less than 1 times 10 to the negative 7th, we know that it is acidic. Okay, but let's first solve for the hydronium by taking the Kw and divide it by our hydroxide, and we end up with 3.1 times 10 to the negative 5th, which again shows me, since it's greater than 1 times 10 to the negative 7th, that this is an acidic solution. 3.1 times 10 to the negative 5th is is greater than 1 times 10 to the negative 7th, which makes it a acidic solution. So both of these happen to be acidic. Okay, now let's talk about pH. Okay, we've been using those exponents, 10 to the negative blah, blah, blah. And we want to have a way to get rid of those 10 to the negative blah, blah, blah numbers. And how do we do this? By logging it, okay? So we can actually get something called pH as the negative log of the hydronium concentration, or the negative log of the H+, the protons. And that's our pH formula. Okay, pH is a measure of the concentration of hydronium or protons. Okay, they're both considered the same. Okay, now you can take the inverse log to calculate the hydronium concentration. So this is an important one to know. You probably don't need to memorize it since you guys are very good at math, but hydronium concentration equals 10 to the negative pH. So that's one way, if you know the pH, to get to the concentration of hydronium or H+. Okay, let's look at this pH scale. Okay, obviously if you have a pH of 7, that's considered neutral. Anything less than 7, the lower the number, the more acidic. The higher the number, the more alkaline or basic. Okay, so a number like 2 would be like stomach acid, things like that, very acidic. Okay, the lower the number, the higher the acidity. Okay, now let's talk about POH. There is a POH scale, and we'll need it to calculate POH, but no one uses it to identify whether something's an acid or a base, or how acidic or alkaline something is. But POH is the negative log of the OH concentration. Okay, but an important thing to note is that pH plus POH equals 14. Okay, that is a really good formula that we used in honors a lot to go between pH and POH. Okay, or you can write it as the pKw is the negative log of Kw. Okay, so the pKw is the negative log of Kw. And we'll be practicing using these formulas in the next couple examples. Okay, so now we got some 4 formulas here. We got our first formula with our equilibrium for water. Okay, we got our second formula, which is getting the pH from the negative log of the concentration of hydronium. We got our third formula, which is POH, getting the negative log of OH. And then, of course, we got our fourth formula, which is POH plus pH is the pKw, which, of course, equals 14. Okay, so let's read this example here together and solve. Okay, so we have a solution that has a hydronium, H3O plus, concentration of 4.3 times 10 to the negative 9. Determine the hydroxide concentration and the pH. Okay, finally, is this acidic or basic? Now, if you're practicing, you could stop the video now, see if you can do it yourself, and then play to see if you get the same answer. Okay, so the first thing we're going to do is use formula number 1. Okay, so we have the hydronium concentration. We can use the law of mass action to solve for the hydroxide concentration, which is the first request of this problem. So we're going to take 1 times 10 to the negative 14, divide by 4.3. My writing's terrible, so I got to fix that. 4.3 times 10 to the negative 9th, and you get an answer, a hydroxide concentration of 8. Apparently I'm taking a long time calculating. I'm not sure what's happening. I think in my notes I had used the wrong number for my exponent, so I'm recalculating. But I get 2.3 times 10 to the negative 6 molar. So that's the concentration of hydroxide, which is what they wanted. Okay, and then the next question is to get the pH. So what formula am I going to use to get the pH? Well, I'm going to use number 2, which I've circled in purple. pH is the negative log of H3O plus, which I have in the given. So I'm going to take the negative log of 4.3 times 10 to the negative 19. Times 10 to the negative 9th. And I get an answer of 8. Once again, I have to redo this one because I think when I first did it, I used the wrong exponent. So I am recalculating and I get an answer of 8.4 as my pH. 8.4 as my pH. Now, I can determine whether this is acidic or basic by looking at 2 things. Number 1, I could look at the pH and say, okay, the pH is on the base side. It is basic. Another thing I could do is look at either my hydroxide concentration, which is definitely less than 1 times 10 to the negative 7th, or I could look at my hydronium concentration, which is definitely less than 1 times 10 to the negative 7th, or I can look at my hydroxide concentration, which is definitely greater than 1 times 10 to the negative 7th. So either way, either looking at those 3 things, I could determine whether it's acidic or basic. Okay, so here we got a couple more examples that we're going to solve. Okay, and we got our 4 formulas listed here. And let's see if we can solve them together. Okay, the first one says the solution has a hydroxide OH concentration of 3.2 times 10 to the negative 5th. Determine the hydronium H3O plus concentration and the pH. Is this acidic or alkaline, aka basic? Okay, so let's see if we can solve that one. So if you want to pause the video and try it yourself. Okay, so we have the hydroxide concentration. Oops, I need to change that. That's not hydronium, that is hydroxide. So let me erase that. Okay, I can determine the hydronium concentration by using equation 1, the law of mass action. So let me do that first. Okay, and I have H3O times OH equals KW. So to solve for H3O, I'm going to take, oops, I got to erase that. I got to put the KW on top, 1 times 10 to the negative 14th. And I'm going to divide it by my OH, which is 3.2 times 10 to the negative 5th for my given. Okay, and I get an answer of 3.1 times 10 to the negative, I can't read my writing, 3.1 times 10 to the negative something. 10th molar. Okay, and since that is way less than 1 times 10 to the negative 7th, I can already tell this is going to be a basic solution. Okay, but let's get the pH first, and that'll also be another way to tell. We'll take the negative log of the H3O plus. So that H3O plus, remember, is 3.1 times 10 to the negative 10th. So we're going to take that. And I get a pH of 5. Okay, well, first of all, I've already determined it's alkaline by looking at the concentration of H3O plus. But I saw for my pH also it's 9.5, which is also greater than 7 on the pH scale, basically saying it's alkaline. Okay, my last problem gives me a pH of 8.1. I need to determine the hydronium and hydroxide concentrations. Okay, so remember my inverse log formula that I can use for pH. 10 to the negative pH is going to be our hydronium concentration. So that would be 10 to the negative 8.1. Okay, which gives you 7.9 times 10 to the negative 9th molar. That would be my concentration of hydronium. And then I could use, I'm going to go up to the top since I'm running out of room, I could use the law of mass action, equation number 1, to find the hydroxide concentration. Okay, so taking 1 times 10 to the negative 14th divided by 7.9 times 10 to the negative 9th. And if I could read my writing, I'd tell you what I got. I'm not sure I'm going to be able to read it, but something times 10 to the negative 6 is my answer. Maybe 13, not sure. Yeah, I can't read my writing. So I got something. 1 times 10 to the negative 14th divided by 7.9 times 10 to the negative